condition describes a wavefront CP striking a mirror, and we have to find condition of theta, which is shown for constructive interference at P. So since it is constructive interference and there is a wavefront, we will be mostly using the concept of path difference, right?
Yeah. So in this question, as he said that we will using the path difference for because for finding the condition for any constructive inference and interference, we need path difference. But in this question, it involves a lot of geometry and geometrical applications and trigonometrical ratios. So basically, we first consider a ray diagram so that it becomes easy for us to get what are the different distances and what are the distance we need to consider so as to calculate the path difference. So basically, the ray AC strikes at O, goes to P. This is A, C, goes to O. This angle is theta, and goes to P. So basically, the waves travel this and this much. The wave travels this from infinity to this path to P after striking the mirror. So, and there is another wave front, and there is another ray which directly goes to B, which is BP, and there is a wave front, and this makes an angle 90 degree. What we'll be basically considering is calculation of delta x, that is the path difference of this ray on this ray. Excuse me. So first we need to see what is. Let's first draw a perpendicular from this to this. Since this are alternate angles, so this will be also equal to theta. Let this point be R, and that as given in the question, this is distance is d. Now ER will be equals to d, PO will be equals to d sec theta, and CO will be equals to PO cos 2 theta, which is equals to d sec theta cos 2 theta. Now the path difference delta x is equals to, as the wave is traveling from here to here to here, so this AC wave is traveling an extra path from PO to OC. This and this, as this is 90 degrees, so this and this part has been traversed extra by this AC length. So the path difference will be the summation of PO plus OC, which will be equals to d sec theta 1 plus cos 2 theta. Now, as we have got the path difference, the only thing left is to for the constructive interference is to compare it with the condition for constructive interference. So for constructive interference, we have delta x is equals to 2n minus 1 lambda by 2, where n is ranging from 1 to infinity, or d sec theta 1 plus cos 2 theta is is equals to 2n minus 1 lambda by 2. So by putting cos 1 plus cos 2 theta as 2 cos square theta, that is one of the trigonometric identities, we get d by cos theta, which is d sec theta, into cos square theta into 2 cos square theta is equals to lambda by 2 into 2n minus 1. So by cancelling this, we get cos theta is equals to lambda 2n minus 1 by 4d. Where n is 1, 2, 3.
White light is used in Young's double slit experiment. The distance between the screen and slits as 1 meter. So that is capital D in the Young YDSE formula. And distance between slits is 0.9 mm, which is small d in YDSE formula. Light reaching at a distance 1 mm above central maxima on screen is passed through a prism and its spectrum is obtained. We have to find the missing lines. So we also have Y in the YDSE formula.
So basically, in this double slit experiment, instead of a monochromatic light, white light is used, which has various components, and each component has a different lambda. So for each lambda, a different diffraction pattern will be obtained, and for each component, there will be different minimas. So what this questions basically, so how could we get the answer for this question? So basically, for every line missing in the spectrum at y equals to 1 millimeter, the lambda for which the diffraction is occurring should have zero intensity of the line at y equals to 1 mm. So first we'll start with the minimum formula of the YDSE, which states that the y, which is the distance of the point from the central maxima, is equals to an odd multiple of lambda d by 2d, where n equals to 1, 2, 3, so on. So after plugging the values of y, distance between the slits, distance of the screen from the slits, we get lambda. We get y equals 1 into 10 to the power minus 3 is equals to 2n minus 1 into lambda into capital D, that is 1 by 2 into small d into 2 into 0.9 into 10 to the power minus 3. So we get lambda equals to 1800 by 2 and minus 1 nanometers. This is in meters. We have converted this into nanometers. Now, by putting different values of n from 1 to infinity, we get lambda equals to 1800, 1800 by 3, 1800 by 5, and so on. So as the wave is a part of a white light, so it must lie in the visible spectrum. So the only possibilities of the lambda are lambda is equals to 1800 by 3, which is equals to 600 nanometer, and lambda is equals to 1800 by 5, which is equals to 360 nanometers. So the missing lines are these: the 600 nanometer and the 360 nanometer.
In this problem, we simply plugged it into the formula for we simply plugged in the values for the formula given, that is for the, and we figured out which minima occur, which wavelengths cause minima at that point, and simply narrowed it down to the only wavelengths which are there in the visible spectrum. In Young's double slit experiment, we are given the data that is small d is equal to 1 mm, which is the distance between the two slits, and capital D is equal to 1 meter, which is the distance of the screen from the slits. Two slabs whose parameters are given, that is, first slab has a thickness 1 micrometer and refractive index 3, and second slab has a thickness 0.5 micrometer and a refractive index 2, are introduced in upper and lower slits respectively. So this is different from a typical YDSE setup, and we are required to find the shift in fringe pattern.
So in this case, as we said that this is different from a typical YDSE setup, as as slabs are introduced in front of the slits, which changes some of the things. So we can't apply directly the formula of YDSE. So as I mentioned in the theoretical part, that if we have introduced a slab in front of a slit, the optical path for that ray increases. So, first see the ray diagram of this. This is the screen. This is center. This is slab. Slabs. Slits. And these are the leaves. Point B. So, in this case, the optical path for S1 will be S1 will be equals to S1P plus, as you remember, it was T into that is the thickness of the rectangular slab into mu minus 1. So this will be equals to S1P plus 1 into 3 minus 1. This will be equals to S1P plus 2 micrometers. Now optical path for S2. So S2 is equals to S2P plus the thickness of the block into the refractive index minus 1, which will give S2P plus 0.5 micrometers. Now, so the path difference delta x is equals to S2P plus 0.5 micrometers minus S1P plus 2 micrometers, which will give the result as S2P minus S1P minus 1.5 micrometers. So hence delta x is equals to y into distance of slits by the distance of the screen from the slits minus 1.5 micrometers. So for central bright fringe, we need to put delta x is equals to 0. As in the central bright fringe, the optical path difference between the two is same. Sorry. As you know, the optical path difference at the central maxima is 0. So for central maxima in the new pattern, maxima, or we could say the bright fringe, maxima, delta x is equals to 0. So which will give me as y is equals to 1.5 micrometers into capital D, which is the distance of the screen, by small d, which is equals to 1.5 millimeters. Now, therefore, the whole pattern shift outwards.
So in this problem, we use the concept of optical path, that is, the path traversed through a refractive through a medium of different refractive index can be substituted with that formula, and then we calculated the net path difference, and then substituted for the respective things, and then for the central maxima we used the condition that path difference should be 0, and then found out how much the pattern shifted there. This is a question based on diffraction. Distance between first and fifth minima of a single slit diffraction is 0.35 mm. So we know that for the values of n being 1 and 5, we have the distance between the two. And screen distance is 40 centimeters from the slits, that is capital D is also given. Wavelength of light used is 550 nanometer. So lambda is also given. We have to find A slit width, that is A, and we have to calculate theta, that is angular position of first minima of diffraction. It's a pretty straightforward question, and I will give the solution.
This question is simply based on the formulas for the diffraction, and we just need to plug in the values in the formula and we will get the answer. Now, so as we know that for the nth minima we have in diffraction we have y of n equals to n d lambda by a, where capital D is the distance of the screen and lambda is the wavelength and small a is the slit width, and n is equals to 1, 2, 3. So basically from question y of 5 is given and y of 1 given, that is the first and the fifth minima is given. So we could that is the distance between the both is given. So basically the distance between the fifth and the first minima will be y the y5 minus y1. So which will be equals to 5d lambda by a minus d lambda by a. So which will give me that 0.35 into 10 to the power minus 3 is equals to 4 into, I have subtracted the equation and plugged in the values, 0.4 into 550 into 10 to the power minus 9 by a, where a is the slit width. So from our, we could directly find out the value of a as 2.51 mm. Now we move on to the next part. In the next part, we need to calculate the angular position of the first minima of diffraction, and we have to calculate the theta. So to calculate, as theta is very small and we know the values of sine theta, so sine theta could be approximated as theta and from that values could be calculated. So basically for small angles, theta is approximately is equals to sine theta, which is equals to y by d, which is equals to lambda by a. So this is lambda is given and a we have calculated in the first part. So this will give me theta as 2.18 into 10 to the power minus 4 radians.